we are discussing in our communication system theory about pulse code modulation. So we were in the middle of discussion of pulse code modulation. In short, it was known as a PCM system. So in our PCM system, as we know, the input analog message signal is is sampled first using a sampler. Okay, specifically greater than or equal to Nyquist rate, and then it is fed to the quantization process. Okay, and you have seen that quantization comes with two flavors. One is scalar and vector. Obviously we don't know how vector quantization looks like because we will not be covering that part of the theory. Scalar quantization, we specifically look for uniform and non-uniform quantization. In uniform, we took two types further. One was mid-thread and mid-rise type of quantization. In non-uniform quantization, we talked about other several types of non-uniform quantization as well. Okay, and we took a few cases of non-uniform quantization in terms of A law and mu law. So to be very specific, so we looked for uniform and non-uniform. Okay, in non-uniform, I talked about A law and mu law in the last session of non-uniform type of quantization process. And as a last step of this PCM system is the encoding process, where all these discrete time, discrete amplitude samples are encoded using in a binary waveform coding system. And finally, these bits are further converted to analog using a process called as line coding technique. Okay, so this, as I told, this will be part of our unit 3. So we are still yet to complete unit 2. We are still in the process of this quantization and encoding itself. As I was describing in the earlier class, the only error in the transmitter. So this is a transmitter part. The receiver does exactly the opposite way of getting back the analog message signal. The transmitter, the only error or the noise in the transmitter, if you have sampled the analog message signal much greater than the Nyquist rate, then the only error involved in this process is quantization error. If you have not sampled according to the Nyquist rate, then definitely there will be noise involved in the sampling process itself. But we take consideration of Nyquist theorem, and all noise or all errors are involved in the quantization process itself. So once this error or noise is involved in this quantization process at the transmitter, the receiver can't do anything. So it will just try to decode according to with the inclusive of quantization error itself. But the recovered message signal will be almost a closer an approximation with respect to the actual message signal which is transmitted. So our job is to reduce this quantization error or quantization noise, so as receiver will predict or demodulate the analog message signal, which will be very closer in relation with the transmitted signal. Okay, so with that idea behind, I will try looking at different forms of this PCM process itself as a system itself, with it to make the system more efficient. Say in reality, when a voice or video signal is sampled, say when voice or video signal is sampled at a rate slightly higher than the Nyquist rate. So obviously we take the sampling process to be following the Nyquist theorem. Say when voice or speech or video signal is sampled at a rate higher than the Nyquist rate, the resulting sampled signal is found to exhibit a high degree of correlation between adjacent samples. So in the sense, when this is sampled, it is found that there is correlation between adjacent samples. So it was assumed that in statistical analysis of all these samples, if we had, we did not do any statistical analysis on these samples, but however, we assumed that the samples generated after the sampling process are independently distributed, if not identical. Okay, so but in reality or in practice, it is found that all these samples, adjacent samples, are highly correlated with each other. The meaning of this correlation or the meaning of high correlation is that in an average sense, the signal does not change rapidly from one sample to the next. In other words, signal has 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 minimum variance. Okay, so the variance are the variations of the signal samples across adjacent, if you consider adjacent samples, the variations or the variance is very less. So when these highly correlated samples are encoded as the process involved after quantization, the resulting encoded signal contains certain redundant information. So with due to this high correlation between adjacent samples, we can say that there is some redundancy involved in the information. So in the sense, we need not encode all the samples. When there is a relation between adjacent samples, why should I be encoding all the samples, or what if I can ignore a few samples in between and transmit only the required information? With that, still I'll be able to record the message signal which can be perceived by the receiver or the human at the other end. Okay, so this kind of signal structure means that symbols that are not absolutely essential to the transmission of information are generated. Okay, so as in a conventional encoding process, you would be encoding all the samples generated from the sampling process, but in this case, by practical observation, that there is a high correlation between adjacent samples, and hence you need not encode all the samples. So what would be the result of this efficient process? Say this efficient process, this will be efficient efficient in coding signals. So this efficient coded signal will obviously occupy less transmission bandwidth. Okay, I can say it will occupy less bandwidth in compared with regular or conventional PCM system. So with this idea behind, how do we try to eliminate, or how do we try to reduce the bandwidth using this idea? So the one flavor or the first type of that process or the type of system is known as differential pulse code modulation. But before moving on to that, we'll consider how this idea is involved in that particular system. Okay, so basically it involves some system known as prediction error filtering. Okay, it's a simple concept which is the heart of your next type of PCM system. Okay, it involves, so if I try to draw the a block diagram of it, say this your input analog signal, say message signal m of t. The first process is to sample it, then the same sample is considered, okay, and it is passed through a block called as a predictor. which actually this is a subtractor which takes the difference of these two samples and generates something known as prediction error. Okay, we'll give this mathematical representation as error as en. So this is your sampler. Okay, obviously at least it will be at the Nyquist rate. Okay, so the output of the sampler can be in discrete form. So this is at every integer values of sampling duration. So we can, in shorthand duration, we can call this each sample as m suffix n. Okay, so we try to take the analog signal. We will pass through a sampler. Each sample is actually passed through a predictor. We'll talk about what is this predictor and the difference between the output of the predictor, so which is denoted as mn hat. So the difference between mn and mn hat is nothing but the prediction error. Okay, the different signal which so compared is called the prediction error. Okay, so correspondingly a filter or the prediction filter that operates on the message signal, which will, this is the one which is involved in generating this prediction error. Okay, so this prediction error is basically a comparator. You can say this is simply compares or it just takes the sample and delays for a certain duration of time in time seconds and tries to compare with the present sample. Say for in other words, say if mn is a current sample, mn hat could be the next sample or the previous sample. So the difference between the current and the future or the past will be the actual error. So if error is large, if prediction error is very large, then we can say that there is high variations between adjacent samples, or there is a high variance. Or if the prediction error is very less, then we can say the adjacent samples are highly correlated with each other, which is actually the prediction error is actually the measure of the variance or the variations between the adjacent samples. So our whole job or the idea behind is to minimize this variance of the prediction error. Okay. All right, so this is the idea of prediction error filtering, where mathematically we can say that, which would be utilized in later part of this discussion. So where mn we have represented as samples of each of these m of t, which denote a sample, then we can say that this error en is simply the difference between the current sample and the predicted sample. Okay. All right. Okay. In other words, en is the amount by which the predictor fails to predict the input sample mn. Okay, so this is the difference between these two samples. How we can try to model this predictor? So obviously, if as long as this predictor is a linear operator, we can easily implement at the receiver as well. So if it's a highly non-linear, then definitely we'll involve will definitely generate more amount of noise or more amount of error in the transmitter itself. So we want this predictor to be highly as linear as possible. So and hence we can say that this mn hat is actually passed through a kind of a linear operator to this mn. Okay, so accordingly we can write this error en as simply the difference between mn and the linear operator mn. Okay, so that I can take this mn as common. This is simply 1 minus L. Okay, or I can write mn in other words as simply 1 over 1 minus L times En. Okay, so all the receiver is to do is to invert this operation. So if this is the expression for the transmitter which generates the error. This would be the expression of the receiver which gets the original sample back. So accordingly, we can try to sketch the receiver block diagram. So this is your prediction error, which is En, okay, which is summed over and with the sample taken to if the prediction or the predictor is the process that we call in the transmitter. I mean, sorry, or the predictor, if I call in the transmitter, similar inverse operation has to be done in the receiver as well. Even that will be a predictor block. But the operation involved in these two predictors will be exactly inverse of each other, and hence the difference between these two will generate your original sample back. Obviously, we have not considered any noise in between the channel. Okay, and if there was any other noise, definitely Mn generated at the receiver will not be exactly identical with respect to the transmitter sample, but this definitely takes out whatever is the prediction error involved in the quantization process. Okay, so this with this idea involved, I repeat, this predictor could be simply a linear operator. It could be a simple one unit of delay function itself, where we delay a sample and try to compare with the current sample and the previous sample. Or if you want to make it more robust or more efficient, we can have this predictor as a series of FIR weights itself, where, say for example, just for the clarity of this predictor block, predictor, I can say predictor filter itself. It could be in big picture, it could be message signal which is incoming, say the sample of the sampled output sampling process. So with a discrete kind of representation, so it could be delayed for 1 unit of time, and the output, if I represent this as Mn minus 1, and say if there are multiple delay units, okay, then Mn minus 1 is passed through, say, certain weights. Say it's called as, I say, W1, it's a first weight. Okay, and then again this Mn minus 2, the second delay output, is passed through, say, another weight W2, and these two outputs are summed, and this process can be continued for various steps, and as a final step you can have final delay block, which is Z minus 1, and if there is a P kind of stages, I can call this is Mn minus P. So the P amount of delays which are involved in this filter process. Okay. And finally I can sum this and get the predicted message signal Mn cap. Okay, so obviously the incoming form this from the previous stage. Okay, so I can involve such P stages, or we can say the order of this FIR filter could be P in most of the practical scenarios. Otherwise I can involve. Yes.
So could you explain again like what the Z inverse means?
Z inverse is the unit delay. It's simply delay in time. Say if message signal, say sample is coming, and you delay, say for 1 unit of time. Okay, if this is message signal, if this is delayed, and I will try to take, say, a difference between these two. Okay, this is mn, and this will be mn minus 1. The difference between two successive samples, so that will be the error. In other words, the error is simply the amount of correlation between two adjacent samples. So this is 1 unit. Say this one z inverse means delaying for 1 unit. If you try to delay for further time, so you will take multiple samples, and the relation between not just adjacent samples, you will take the relation across several samples at a time. So if you consider such kind of complex scenarios, obviously the predicted output or the predicted mn cap would involve less amount of information compared to the original message signal. So this number of orders, or the number of p keeps on increasing. Obviously your message keeps on getting compressed, in other words, where say if 4 bits or 8 bits per sample, if it is needed to encode the original message signal with the usual sampling process, probably you will be needing just 4 bits per sample in one, if you try to compress or if you try to eliminate all the redundant information in a message signal, where there is a high correlation across the samples. For just simplicity, you can just assume that this z inverse block is simply a delay in time. Okay.
So basically, like the more the delay, then the less the number of samples.
Exactly. In the sense, more the delay, in the sense you will consider more number of samples of the future. Say if say there is a 5 seconds of duration in the prediction of sample, I'll take one sample at first unit of time, and I'll consider all the samples in this process, say m3, m4 up to m5, and I'll try to find the relation of m1 with respect to with respect to all these samples. Or in other words, I'll take current samples to be m5. What would be the error involved, or what is the correlation between m5 and m1, what is the correlation between m5 and m2, what's the correlation between 3 and 4 as well. So I'll consider all these correlations, and I will come up with one sample. Simply I can say m5 cap. Okay, so this will involve, instead of sending 5 samples in 5 seconds of duration, I'll just simply take one sample by eliminating all the other 4 samples which are unwanted or which are redundant in my transmission of the message signal. Okay. Okay, fine. So with this idea in our hand, we'll try to define our new pulse coded modulation technique, which is known as differential pulse code modulation. Okay, in short, we call such system as DPCM. Okay, so the only the difference between the previous linear predictive filter or the prediction filter that I had addressed earlier, where I was predicting directly on the message sampled itself, but the only difference in differential pulse code modulation is we perform prediction on the quantized sample. Okay, so this process involves an extra additional kind of blocks between the quantization and the encoding process. So I will be doing the prediction on the quantized sample, not on directly on the message signal. That's only the difference. So in the sense, say this is error en, which is coming due to the prediction. What I do is that I will pass through the quantizer, which due to the quantizing process, there is already an error which is generated from the linear prediction. Okay, So the error involved within the quantizing process, I'll add with a suffix q here, where q stands for the quantizing error. So error e suffix n is the error involved in the prediction based on the message sample. Okay, I'll take this sample, the quantized sample, and I'll try to add it with the predicted sample, which is mn cap. Okay, and then finally I'll pass it through. You understand this process once I take it mathematically as well, and I'll take it to a linear predictor block. Okay, I'll specifically say this as a linear predictor, and whatever you generate will be the final sampled output. So to complete this understanding of the differential pulse code modulation, the differential is with respect to the differences between the adjacent samples. So this is actually the structure involved in differential quantizer. Okay, so this is a structure, is not regular quantizing process, unlike in your PCM system. So this is the quantization process on the difference of the samples, and hence this is known as differential quantizer. Okay, so in order to say this theoretically, we need to perform, or the motivation behind this differential quantization follows based on two practical observations. One is, first is that we need to perform waveform encoding in the transmitter. So this is known as line coding, where we need to convert all the bit streams into pulses, into waveforms. So we need to perform this waveform encoding in the transmitter, which requires the use of quantization. Okay, and obviously the receiver, the decoding in the receiver, okay, which has to process on a quantized signal. Okay, so based on this two motivations, and to make the transmitter and receiver process exactly inverse of each other, where we need to since the process involved between the quantization and the encoding needs to be exactly the same fundamental principle in the receiver in opposite manner. To make the process very simpler, we will be taking this step for the DPCM process. So the block diagram, the complete structure of differential pulse coding modulation looks something like this, where you take the sampled version of the message signal. I will not write, I'll just say simply as mn, and with your comparator you basically compare with, I'll try to write later. As we know that this is sampled signal, which is subtracted or which is compared with respect to say 1 unit delay of a sample itself, which is incoming here as mn hat. Okay, so the quantization has to be done on the error signal, not on the message signal. Okay, so this is a quantizer. Okay, and finally, as the step involved in our PCM system is encoder. Okay, encoder process, and finally you call this as DPCM encoded, we can say signal we'll represent this, in a mathematical notation as mq suffix, mq comma n, where the output of this quantization or quantization process is involved with, a suffix or subscript known as, q, which is taken and added with the prediction. Okay, don't worry, you'll understand this. This is your linear predictor. Okay, so the linear predictor actually performs the prediction on, not on the message signal. It performs the prediction on the quantized sample, which gives you a prediction, back to the system. And here, obviously, this is an adder, this is a comparator, this is an adder, as you can see. The input of the predictor is not simply the sample mn. So input of the predictor is actually the message sample, but it is a quantized sample, and hence it is, given a suffix or subscript known as, q comma n, where the relation between several mathematical representations here is that where u q comma n is nothing but en plus the quantization noise in the upper path, in the straightforward path, where q suffix n obviously is actually the quantization noise in the quantizer process itself. So if I try to write that, quantization qn is the quantization noise produced by the quantizer, or you can say in quantizer. Okay, and this is basically the output of the quantizer, which involves the error due to the prediction and the error due to the quantization process. And m q comma n, okay, this is the part which is actually getting into the linear predictor block, which is actually, as you can see, this is a feedback loop where the prediction on the message signal is getting back to the summer or the adder here, which is the addition of the predicted sample plus eq comma n itself. Okay, where mn cap is, where mn cap, as we have introduced in the previous part, is the predicted value of the original message. In the sense, we say that the next sample in the process is which can be predicted, or can be predicted based on the correlation between correlation across the adjacent samples. So with that high correlation assumption only, we can try to predict what will be the next sample which is incoming into the system. Okay, and obviously if you can replace this mn cap is nothing but, mn cap, where eq comma n is can be splitted from, taken from this previous equation, which is the error in the prediction and the quantization noise. And as you know that with the linear prediction theory involves the summation of the prediction, and the error involved is nothing but your original message signal itself, or the sample itself, plus qn. And hence this final expression demonstrates that the output or the input to the linear predictor is actually the quantized version of the original message sample mn itself. Okay, so this says that quantized version of the original message signal itself, original sample to be specific. Okay, So that's how our linear prediction or the differential pulse coded modulation looks like. So summary about this process is that the transmitter, the DPCM transmitter, actually works on three steps, iterative of three steps. First is given the predicted message signal. Okay, this stepwise will be easy to understand and which complements the block diagram above. Given the predicted message signal, okay, let us take the predicted message signal as mn hat, okay, which is the output, actually the output of the comparator, which will take compares the comparator at the transmitter input, computes the error. Okay, this mn hat is taken. Okay, this mn hat is taken, which is the output of the linear predictor, compares with the current message sample, and with the comparator will produce an error in the comparison or error in the prediction, which is known as en. Okay, so this is at the transmitter input, which computes en, which is quantized. Then en is quantized to produce the quantized version of en, which is we have predicted, we have denoted it as EQ comma n. That would be the first or the upper path which describes this process. The second path, second process involved in DPCM transmitter is with this mn cap and quantized error. Okay, with these two quantities we can have the adder or the summer. The adder actually in the transmitter produces the quantized version of the original message signal mn. Okay, so this produces quantized version of mn. We call this as mq comma n. Okay, and finally at the end we'll have one step prediction. We'll have simply one step prediction involved in the linear predictor block prediction. Mn cap is produced at the finally. Okay, so that if you have say order of p of your linear predictor filter, simply it's a FIR filter itself. You can have several samples which are delayed for several unit of delay, which that you can say the lossy the compression will be further, and you may have to incur more number of losses in the original information signal. Okay, so the multi-stage operation is basically this is a cyclic operation which fundamentally involves these three steps irrespective of the order of the filter that you choose. If the more is the order, I can say if p increases, your message gets compressed, and we can say it's a kind of a lossy compression. Okay, so lossy compression doesn't mean that you will be losing out the original information of the signal. Definitely you will be losing out in terms of the samples produced, but all in all you will be retaining whatever is required for the transmission. Only prominent information of the original message signal is required to encode and transmit through the channel. Okay, we need not encode all the samples involved in the message signal with again going back to the same fundamental theory that there is a high correlation across the samples in original message signal, especially in case of speech and video processing. Okay, DPCM receiver does the exact opposite job. So I can say that it involves the exact inverse of this operation. We can say that it receives a noisy, if there is a noise involved in the channel, I can say this is a noisy version of DPCM encoded signal. Okay. This first job is to decoder. Okay, so that is the first step in the in the receiver part. Then you try to invert like the linear predictor in the transmitter. Okay, so do the inverse operation where the receiver also involves a linear predictor. Okay, it's possible on as long as your prediction is linear. Remember, if it's a highly non-linear process, then definitely you may have more efficient system, but that doesn't guarantee that you will decode or demodulate the original information back as it is transmitted from the transmitted end. Okay, so finally you will get a DPCM decoded signal. Okay, that's how the process is involved in the receiver, which is the exact opposite of the transmitter end. Okay, so that's how I can summarize the involvement of a slightly modified version of our original PCM signal. Of course, just writing the working principle of any system doesn't serve a complete process. We need to have certain parameters which will evaluate or which will give the quantitative analysis of any system. So to evaluate any DPCM process, there is something known as processing gain. Okay, this is one of the important terminology used in most of the digital communication theory. You will see in as the course progresses, but it's good that we try to introduce this term right away, such that you will remember that this is one of the important performance parameter which is used to evaluate any system, in particular in our case PCM system. The processing gain involves the actually it's in terms of the signal to noise ratio at the output of this quantizer. So output of this DPCM complete system, which we can say that it's a ratio of signal power to the noise power. So signal power, we know that we express the power in terms of variance itself. We can express the signal power to be sigma square suffix m, where m stands for the message sample or the random variable m of t, and to the noise, which we know that noise involved in our entire process is the quantization noise itself. So we can represent it as sigma q square. Okay, where this is actually the message. I can write it specifically. It's a variance of the message signal. Okay, we have assumed it to be zero mean. Okay, we have all along we have assumed it to be zero mean. If it's a non-zero mean, we can still perform for the zero mean and finally add the mean to the final value that we obtain. Okay, even the signal to quantize, the quantization error which involves in the process, we have said that the denominator sigma q square represents quantization error, which we also assume it to be a zero mean, and hence the ratio of these two quantities is a meaningful one. We can rewrite this ratio of signal variance to the noise variance. We can rearrange this ratio as sigma square m over sigma e square times multiply and divide by a quantity sigma e square, where sigma e square is the variance of the prediction error now, because the process doesn't involve just transmission of sampling to quantized output. It involves an intermediate step of prediction. Due to that prediction, you have incurred an extra error, an additional error in form of prediction error itself. So we need to have a quantity which describes that error as well, where the sigma e square is actually variance of the prediction error En itself. Okay, and finally we can express this compactly. The signal to noise ratio is actually can be written as the first ratio, which is sigma square m to the sigma square e, is known as the processing gain, which is short in shorthand notation it is known as GP, and times, obviously we know this can be represented as simply as signal to noise ratio of the quantization process. Okay, because the quantizer doesn't take now the message signal. Quantizer input is the error signal E itself, and hence the output or the performance of the quantizing process is nothing but the ratio of variance of the error signal to the quantization error or the quantization noise, where this GP is known as the processing gain. Okay, this evaluates what is the actually the process involved in the prediction, how efficient it is. It actually evaluates the complete linear predictor part. Okay, so this in particularly this is the ratio of message variance to the error variance. Okay, so now in the case of voice signals, it is found that the optimal signal to quantization noise ratio, this SNRQ, when you compare with respect to the regular PCM, okay, in comparison with, I try to compare with conventional PCM, okay, in comparison with in conventional PCM, we need to how will you compare now? So if you compare with a conventional PCM, if you compare DPCM, you'll have to have signal to noise ratio output as it is depicted in this equation. The performance of PCM system is evaluated as SNRQ itself. Obviously, there is a difference in signal to noise ratio. Okay, so if GP is greater than 1, and obviously you'll have signal to noise ratio to be higher than compared with signal to noise ratio of the regular quantization process, and hence it's that if you try to compare these two terms with respect to their actual values, it is found that it is around 4 to 11 decibels amount of the increasing amount of performance that may be obtained using DPCM system. Okay, these on based on experimental studies. It appears that greatest improvement occurs in going from no prediction to first order prediction. Say in no prediction is in case of PCM. Say there is no prediction involved here at all. Say if there is no prediction and there is at least one prediction or the first order prediction with some additional gain in terms of GP which can be obtained. So this GP keeps on increasing, the processing gain GP increases, and hence your signal to noise ratio keeps on increasing, or the more efficient system that you may be design as you increase the order of this linear prediction filter itself. Okay, so if you go up to filter of order 4 or 5, which so that's how I can say about the advantage of the DPCM process. So this, if it is in terms of its performance, in terms of its the occupancy of the bandwidth, if I say if a regular PCM, if it takes 1 bit per sample, okay, if a regular your PCM system per sample, if it takes 1 bit, your DPCM can, okay, DPCM actually I'm sorry, so if your PCM takes say around say 8 bits per sample to represent, since there will be many samples to represent, your DPCM may take just half of it. Okay, there could be simply 4 bits per sample due to reduction in the amount of samples itself. Okay, so that's how I can talk about the process involved, DPCM process. So this is one type of, a variation with respect to our regular PCM system. Another PCM system that we'll be dealing in the next session is, delta modulation. So more and more we try to deviate from the regular PCM system. More and more we'll be moving towards the algorithms which are involved in the practical quantization process, which will be the, part of when we try to end this unit with respect to, voice encoding process. Okay, so I'll try to take, an actual voice sample and try to showcase the quantization process and encoding process involved. Will At the end of this unit 2 is my idea to give you a demo on this chapter which involves all the process.